Or, as I said, feel free to jot some things down if you want to. Keep those calculus glasses on. And do you see where the slope is increasing? Well, maybe I shouldn't word it that way because I haven't talked to you about this yet, but I want to show you what I mean by the slope is increasing. Now, just by the way, the slope increasing is not the same as the slope being positive, just in case that's crossed your mind in the last 10 seconds, but it does mean what it says, the slope is increasing. I'd like to propose to you that everywhere in this green section, everywhere in this green interval, the slope is increasing. Remember, this is a preview, so if you're like, huh? What are you talking about? Well, look at what happens to the slope as I go from the beginning of this green interval to the end. Here, the slope is very negative. Here, the slope is a little less negative. As I keep traveling along this interval, look what's happening to the slope. Well, it's becoming less negative, and in fact, it would be increasing. You see, the slope would be increasing because it keeps getting bigger. Do you agree with me? If you move along this interval, a slope that was negative is becoming positive and in fact is increasing the entire time. Okay, that green interval, according to our slope glasses, would say increasing. The slope is increasing. That's something that we will talk about in much more detail near the end of this chapter. Okay, so I know for some of you this might bug you because I'm showing you some stuff and I don't necessarily expect that you fully can reason it, but I still want to show you. How about where the slope is decreasing? The slope is decreasing. I'd like to propose to you that that's happening everywhere in this yellow interval. Now, maybe you're not surprised, but let's visually see what's happening in this yellow interval because the slope is very positive. As I move along, though, the slope is less positive. There actually is a point where the slope is 0, but as I keep moving along this interval, what's happening to my slope? Well, it keeps decreasing. It keeps becoming more negative. So everywhere from this point all the way to the end of the yellow interval, my slope is decreasing. Okay, and that is a special, basically a special concept that we will use derivatives to further analyze. We will use derivatives to further analyze. That's not all. How about a positive slope? How about a positive slope? Now, positive slope would mean that the rise over the run is positive. This one sometimes is a little bit easier to grab onto. We've actually talked about this a little bit, but simply everywhere in this interval, everywhere in this blue interval, my slope, my rise over my run, the tilt of this line is always positive. Okay? Positive, very positive, but still positive all the way along here. Interesting. I just want you to observe this. I don't expect you to fully understand it, but observe it with me. These intervals overlap. In other words, I can be positive, like blue, but I can be decreasing, like yellow. So I can have a positive slope, but it can actually be decreasing. That we will definitely expound upon Okay, that's something that takes some time to understand. Wait a minute, what does that really mean? I just want you to notice that they overlap. Negative slope. Negative slope. It's the only section that we haven't colored twice. But look, everywhere in that section, everywhere in that interval, the tilt of my line, the rise over the run, is negative. Same thing over here. Okay, definitely every slope in this orange section is negative. Negative slope. Increasing slope. Huh? Negative slope. That's the orange section, but yet it's increasing. Again, those are two different ideas, and they often take some time to process. But we've got the power of derivatives to be able to help us do that. And of course, there's some other things that I'm going to show you. It's pretty neat how this applies to a word problem. I told you we're not going to do a word problem right away, but it is pretty neat when you realize what we're doing here and how that does connect to the real world. And sometimes it's not until you finally get to calculus where you start to really see some real connections. So if you were hard on your teacher like back in 9th grade and you were like, when am I ever going to need this? Okay, we're getting to that point where we will use it. So maybe go back and tell them once. But sometimes you have to get to more advanced math until you start to actually apply it. And we're at some of that spot here, so it's a neat place to be. Let me give you one more preview. Okay, appreciate your attention. This is like a preview of the whole chapter. But maximums and minimums become part of that preview, part of that chapter. And I would bet that out of everything that we said here, that you would feel like you have the most sort of experience with, right? Maximums and minimums. Like, it's probably not a huge shock if I point at point A and tell you that that's a maximum. Okay, if I'm standing at point A, I'm standing at a high point. But it's not the absolute maximum, right? Point C is the absolute maximum. So what is point A? Well, it's a relative maximum. It's a relative maximum. There's something true, though, about both of these. Let me rephrase that. There's actually something different about both of these. This point was an endpoint. Now, an endpoint, like point A, ends up being, again, a maximum. Or like this endpoint, this ends up being a minimum. But I just want you to notice that endpoints are maximums and minimums. And then there was something different about this point C, or about this point B. Now here's your little calculus connection. This is what we're going to spend most of the period today and Monday talking about. A critical point, a place where the slope is equal to 0 because it changed from positive to negative. Now, take this in. It's not hard, but it's like a major idea that point B is a critical point because the slope changed from negative to positive. And here you can see that it clearly has a slope of 0. Same thing here. It has a slope of 0. Now, maximums and minimums become the conversation for our first section, okay? Our first section of this chapter, which we're going to kind of officially start here, where we talk about extreme values. Now, I would say if you haven't jotted something down, use that pencil. We're going to talk about extreme values. Now, extreme values are really just a somewhat fancy word for maximums and minimums. And we can have absolute or relative maximums and minimums. Make sure you get this, though. I don't know. There must have been a time in the past where, like, maybe I didn't teach this well or somebody just didn't pay attention, but they didn't understand when I said extreme values, like what we were talking about. So I want to make sure that doesn't happen again. An extreme value, I mean, it's kind of a fancy word, but it's literally talking about the maximums or minimums of a function. And I know you've talked about this back in an algebra or trigonometry class, but to make sure we understand absolute, I use that phrase quickly, but absolute is the highest or lowest. Maybe that's kind of common knowledge to you. And then relative would be not the highest or lowest, but more like in the neighborhood. So we can distinguish between absolutes and relatives, and actually that becomes a simple problem that we can do. Why don't we do it for that graph? So I guess if you didn't sketch that graph, you might want to make a quick sketch of it. And again, this is probably one of the easier things that we do this year, but if I look at that graph over there, as we already said, the absolute highest point is point C. The absolute highest point is point C. The relative maximum, though, is point A. And just to make sure that I'm not just kind of glossing over this, when we say that point A is a relative maximum, it's kind of like we put an imaginary circle around it. The size of the circle depends on the shape of the graph. But the point is that within that neighborhood, point A is a high point. You should be saying, but Mr. Naylor, there's higher points over here. Yes, but in the neighborhood, point A is a maximum, and that's why we call it relative. The book calls it a local. The book likes to use the word local. Point D is absolutely the lowest point. Pretty basic stuff there. And then point B ends up being one of those relative minimums. All right, nothing too earth-shattering right now, right? Okay. Let's do something that calculus likes to do. It likes to notice things that are always true. We call them theorems. What if I change this graph? I don't even want to say a little bit, because I've actually done something pretty significant here. But what if I change the graph and basically no longer does it have endpoints? The truth be known, I could erase point A and D because they're really not significant anymore. But something else has changed, not just erasing points A and D. Something else has changed. They're not there anymore. A focusing on the word absolute doesn't exist anymore. There is no absolute maximum, right? I mean, look, point C is no longer the highest point. In fact, the truth is there is no highest point. Point D, I mean, we kind of erased it, but the truth is there's no absolute minimum anymore. And what just happened here is that we, I suppose, kind of in a backwards way, discover that if you do have endpoints, let me say that again, if you do have endpoints, you will always be guaranteed an absolute max and min. Sort of on the contrary, if you don't have endpoints, you won't be guaranteed an absolute max and min. We call that, oh, shoot, I forgot I had this little screen here, this little sentence here. I need to show you the word extrema, a little bit out of sync here. Extrema is just a plural for absolute or for maximums and minimums. So if somebody asks you to find the extrema, okay, that's just a word that means find the maximums and minimums. I forgot that I had that there. It's not a misspelling. It's just plural. Now I lost a little bit of the punch for what we were just doing there. But if you have endpoints, you are guaranteed an absolute max and min. That's called the extreme value theorem. The extreme value theorem. Let me step back here. This is an important idea. It's a little bit wordy, but I wanted to give it to you. Look at what it's saying. In essence, if you have endpoints, that's kind of like what's written in white. If you have endpoints, if you have a closed interval, now a closed interval means endpoints, then you will have an absolute max and an absolute min. It's actually, if you think about what it's saying, it's also not that earth-shattering, but it's always true. All you have to do is close up a graph, and you will have an absolute max and min. And just like we did over here, on the contrary, if I open up the graph, okay, it's not closed anymore, I opened it, then I'm not guaranteed to have an absolute max and min. Okay, in fact, for this problem, I end up with neither an absolute max or min. There's one more thing to show you with this, but it looks like we'll just do it when you return.